Hey guys, happy snow day. So, chapter 7 brings us to applications of integration. Some of them are going to feel a little bit more application-y than others. I feel like 7.1 is kind of pretty straightforward. Area between two curves. The good news is, works exactly like you think it should work. So, for example, I'm going to bring you to this little picture down here, right? Find the area between the two curves f and g over the interval ab. So we'll call this blue one f, and we'll call this red one g. You're going to have to forgive me. I left my stylus at school, so my handwriting's going to be pretty atrocious. Right, so we want the area between the two curves. So that would be this region right here. And it works exactly like you think it would work. So actually, let me undo that at the moment, right? Erase all of this. Right, and you could probably figure, right, that the area between those two curves is going to be the area under curve F, right, total area, right, measured with respect to the x-axis, minus the area that's under G, right? If we subtract this portion, that will leave us with exactly what we want, right? So I guess you could say, right, more succinctly, that we can take the area under F from A to B and subtract, right, the area under G from A to B. All right, and we know that there is a property of integrals that will let us handle this a little bit more succinctly rather than doing two separate integrals. We could actually, technically, do it as one, right? We could just say integrate from A to B and integrate the difference of the two functions. I mean, you could do it as two separate ones, but anytime that I can be a little bit lazy, I probably will. Right? So it's as simple as that. All right, now, I mean, really, there's no trick to it. It's exactly as easy as it sounds. However, there are a few strange cases, so I'm just going to take you through a couple of those to make sure we've covered all of our bases. All right, so if you go to the next page. All right, this is sort of the simplest case. All right, this is what you hope you get because everything's pretty much just nice and laid out for you. All right. The simplest case will be something like you saw in the previous setup when your limits of integration are going to be given to you explicitly and all you have to do is set up the problem. All right, so find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Okay, so y equals x squared plus 2. Well, that's just a parabola. Right, it's a little concave up parabola. I'm just going to draw half of it, and you'll see why in a second. All right, so, all right, let's just draw from here up. We'll call this y equals x squared plus 2. All right, the other line is y equals negative x, and so that's actually going to go right through the origin, right? So we're going to be looking at something like this. Okay, fine. All right, and then they give you these two vertical lines, right? They give you x equals 0, which is right along here, and x equals 1, which will draw in right there. And so there's the line x equals 1. And so you can see the region that we're looking for, right? It's the region bounded by all four of those curves, which would be this spot right in here. And so now all we have to do is set up the definite integral. All right, so, woo! All right, so let's take a look here. All right, let's see what we can do. All right, we're going to, all right, so take the top curve and subtract the area underneath the bottom curve. That's actually going to be negative area in this case. That's fine, no big deal. All right, so we would write, written as two separate integrals, it would look like this, right, from 0 to 1. And then we would have the top curve, which is x squared plus 2. And then we would be subtracting the bottom function, which is just the line y equals negative x dx. And that's perfectly valid. You could do the two different integrals, right? But that's going to take you, you know, twice as many steps, in my opinion. So let's condense this a little bit. All right, let's just say that that's going to be from 0 to 1, and we'll have x squared plus 2 minus negative x. So I'm going to say plus x dx. And then we just need one integral, and that's a little better. Okay, so let's do the definite integral. All right, let's see. X squared will integrate to x cubed over 3. 2 will integrate to 2x. And x integrates to x squared over 2. I know this is tough. And we evaluate all of this between 0 and 1. And we love this because our second term is really just going to drop out here, right? And so let's see. All right, so that will give us 1/3 plus 2 plus 1/2 minus 0, just so we see where everything went. All right, and let's see, 1/3 plus 1/2, that's 5/6. So that's going to be 2 5/6. Or whatever your improper fraction equivalent was. Check that on your calculator, though. Not too bad, right? Well, okay, yeah, of course, it gets a little bit more complicated, but it's not too bad. All right, so let's go to the next page. All right, so it won't always be as clear as, oh, go from x equals this to x equals that, right? Sometimes you're going to have to do a little bit of legwork in order to figure out what your limits of integration need to be. All right, so example 2 says find the area of the region bounded by the following graphs. So we'll have this concave down parabola, right, with a y-intercept and a vertex at 2. So we'll have something like this, more or less. All right, and then you have the line y equals x. Doesn't really get much easier, so off you go. All right, and I should probably label these. This is y equals x, and this is y equals 2 minus x squared. All right, and so now it's the region bounded by the graphs. So it's the region enclosed between them. So that would be this area right here. All right, and that's all well and good, right? We'll do top curve minus bottom curve, and then the question becomes, ooh, well, what do we integrate between? What are our limits of integration? And if we just look at the picture that we've created, it's a pretty easy fix, right? We just need to integrate from this point to this point. So all we need to do is find these x values right here, right? From A to B. And fortunately, that's as easy as finding where do these two curves intersect. All right, so let's set up a little side problem here, right? So we want to know where does 2 minus x squared intersect with the line y equals x. All right, so we'll say, well, they gonna need my pen. All right, they say that 2 minus x squared, right, will intersect the line y equals x. Where are they equal? All right, and if we do a little bit of factoring here, right, so we'll get x squared plus x minus 2 equals 0. This works out pretty nicely, right? When we factor, let's see, we're just going to have, let's see, a positive 2 and a negative 1. Good. Right, so that gives us x equal to negative 2 and x equals 1. So good, we've found the limits of integration, right? And so those values are, right, actually, right, negative 2 and positive 1. And so now we're good to go ahead and do the actual calculus part. All right, so let's set up our integral. We know we're going to be going from negative 2 to positive 1, and we will be doing top curve minus bottom curve. All right, the blue curve is consistently on top throughout the whole thing, right? So we can say 2 minus x squared, and then minus our bottom curve, which is just x. So that's nice. All right, and then we'll integrate. All right, 2 integrates to 2x minus x cubed over 3 minus x squared over 2, and we'll evaluate this thing between negative 2 and positive 1. All right, and the value of this at 1 is 2 minus a third minus a half minus, let's see, negative 4 minus plus 8/3, I think, and then minus 2. All right, let's see. Okay, so let's clean this up. Let's see, well, negative 1/3 minus 8/3, that's negative 9/3. That works out pretty nicely. Let's see, 2 plus 4 is 6, plus 2 is 8, right? Minus a half, that's plus 7.5. So we end up with negative 3 plus 7.5, which gives us a grand total of 4.5. All right, so the name of the game here is that if your limits of integration aren't explicitly stated, you might have to do a little bit of algebra to figure out your endpoints. Not a huge deal. Okay, so this is exactly what it sounds like. Sometimes which curve is on the bottom and which curve is on the top are not necessarily consistent throughout the course of the problem. All right. And like I say in this paragraph, right, this usually happens if the graph intersects in more than 2 places. All right, so let's take a look. Let's take a look at this right here. Find the area of the region enclosed between these 2 graphs. All right, so we've got y equals the cube root of x minus 1. And if we remember our transformations, that's going to actually be a horizontal shift right 1 of the cubic root function. So helps to know your graphs as well. Otherwise, you might not necessarily pick up that they intersect in more than one place or that the top and the bottom curve switch. So we're going to get something like this. All right, and that's y equals the cube root of x minus 1. All right, and then you have the line y equals x minus 1. All right, and I'm pretty sure, right, that this point right here is negative 1. Let's just double check, right? If that is negative 1, then in this function right here, when x is 0, I should get out negative 1, right? Y-intercept and all. So yeah, right, when x is 0, cube root of negative 1 is negative 1. Great, so they intersect right there. I'm also pretty sure that they'll intersect there-ish, but you know, we'll verify all of this with some maths. All right, and so there's the line y equals x minus 1, more or less. All right, and so now we can see we actually get this interesting area, right? It's the area of the region enclosed between those 2 curves, and so that's going to be right here, this little portion, and this little portion, right? And we can see, right, in that first small portion, the line is on top, whereas in the second small portion, the curve is on top. So this you will have to handle as two separate integrals. Is just the way it is. You just always want to make sure that you're doing top curve minus bottom curve. All right, but again, we're at this point where we need to find our limits of integration. So we need to find the points of intersection. And now you could go through all the trouble of setting these two things equal to each other and cubing your binomial, but I mean, hey, I already know one of them, right? This is the point 0, -1. Let's see, I suspect that this is the point 1, 0. Let's check and verify if I am correct, right? In both of them, if I plug in 1, I should get out 0. Works for my line, works for my curve. And then I'm pretty sure right up here, this is the point 2, 1. Right, let's just check, right? Yeah, when I put in 2 into each of them, I should get out 1. I mean, of course, you could go ahead, set these two curves equal to each other. It's just a little bit more algebra than I care to do at the moment. So let's get to the good stuff. Let's get to the calculus. All right, so our first piece, all right, is going to go, right, from x equals 0 to x equals 1. That'll be line minus curve. And then our second piece is going to go from x equals 1 to x equals 2, and that's going to be curve minus line. All right, so this is just really, it's really going to be an exercise in bookkeeping is all. All right, so we're gonna have two integrals, right, and we'll be adding them together. We will be adding their areas together, although if you notice, right, it looks like the two areas are probably equal, right? However, be careful. This doesn't mean that the total area is going to go to 0 necessarily, all right? Because we're talking about area between curves, not necessarily relative to the x-axis. So yes, they look like they might be about equal, but I wouldn't jump to the conclusion that your total area is going to be 0. All right, so let's go ahead, let's do it. All right, so we are going to have, right, so our first area rather, is going to take us from x equals 0 to x equals 1. And in this case, our line is on top, and we subtract the bottom curve, which is our cube root function. And then we will add that to the total area enclosed from the second piece. So we'll go from 1 to 2, and now our cube root function is on top, and we will subtract the line. I'll just throw the dx out here. Alrighty, so let's get to it. All right, these first two terms integrate really easily, right? X goes to x squared over 2, -1 goes to -x. And if you notice, for this piece right here, we could use a u sub, but at the end of the day, we would probably let u equal x minus 1, and then du dx is 1, so du and dx are equal, so you can just do a direct substitution, which means I can pretty much just do reverse power rule on this thing. So I'm going to say minus, and then I'll have x minus 1. Well, let's see, it's to the 1/3, so when we add 1, we'll get 4/3 over 4/3, which means times 3/4. Okay, and we'll have to evaluate that between 0 and 1, and then add that to this second piece. Fortunately, the integration is going to be the same because you have the same expressions, right? So the cube root of x minus 1 will integrate to x minus 1 to the 4/3 over 4/3, right? And then minus x squared over 2, and then plus x when we distribute that negative, and evaluate everything from 1 to 2. All right, let's come back over here and do my least favorite part, the arithmetic. All right, so the value of this thing at 1 is going to be 1/2 minus 1. And then you'll notice that when x equals 1, this second piece goes to 0, so that's nice. And then we'll say minus the value of the function at 0, which will be 0, minus 0, minus, let's see, when x is 0, we'll have -1 to the 4/3, which is the cube root of -1 to the 4th. So that'll be +1. So then that'll just be minus 3/4, and I'm just going to stay over here and clean this up really quickly. All right, so 1/2 minus 1, that's -1/2, and then this will become a plus 3/4. So that's going to work out to a quarter. All that work for a lousy quarter. Alrighty, let's swing on over here, and we'll evaluate this thing at 2. We'll put a little plus sign in between. All right, so the value of this at 2, when x is 2, this first term, I'll have 1 to the 4/3 times 3/4, so 3/4, minus, let's see, 2 squared over 2, so that's 2, plus 2, minus this thing evaluated at 1. So when we let x go to 1, our first term goes to 0, minus a half, plus 1, and then we'll tidy this up. You guys cancel each other out. So I will have 3/4 minus positive 1/2. Oh, look at that, a quarter. So at the end of the day, we will be adding a quarter plus a quarter to give us a grand total, a grand glorious total of 1/2. All right, so again, it really helps to have, a working knowledge of your functions and graphs. Otherwise, you might not necessarily be aware of the situation that you're looking at and that the curves are switching and there's all this fancy stuff happening. All right, one last example. Next page. Okay, so this is going to maybe feel a little bit uncomfortable at first, but it can make your life so much easier. All right, so I'm just going to take you through this little narrative up here, right? We sort of always integrate with respect to the x-axis, right? So we find the area between some curve measured relative to the x-axis. And maybe that's what the problem asks us for, right? Maybe then we want a problem where we're measuring relative to the y-axis for whatever reason. That's what they're asking us for. Right, so we can do that, all right? However, in the case of area between two curves, area is area, right? The area enclosed between the two regions it's the same, and it shouldn't matter which way we measure, right? Whether we measure with respect to x or with respect to y. However, sometimes it's easier to do it one way versus another. All right, so I'm going to take you through 2 examples, right? I'll do it first with respect to x, like we would normally do it. Then we'll do everything with respect to the y-axis, and you'll see that it's actually easier doing it with respect to y, okay? So example 4 here says find the area of the region bounded by the graphs of x equals 3 minus y squared and y equals x minus 1. All right, so we kind of look at that. We look at this and we're like, what? Why? Okay, fine. Let's solve for y in terms of x. All right, and so when we do a little bit of algebra here, we would get that y squared equals 3 minus x, I believe. Yeah. So y will be plus or minus the square root of 3 minus x. And so really what that figure is going to be, it's going to be both the positive and negative halves of the square root function. Because of the negative x, right, it's going to be reflected, all right? And we're going to be left with the curve that looks sort of like this. Okay, and now, so that is going to be y equals plus or minus root 3 minus x. The second curve is much easier, okay? You'll have the curve y equals x minus 1, which is going to be basically this right here. And so we would be looking for this enclosed area right here. Okay? And so we would have to find our limits of integration by setting them equal to each other, right? And then you realize that you sort of have a difficult thing to do, right? Because for a while, the line is on top of the curve, and that's fine, right? I would say from here to here, we're in business, right? We can just integrate line minus curve, and we're good. But then there's this second piece, right? Where it's really just the area under the curve, right? The area under the square root, and then you have to handle this plus or minus thing, and right? So it quickly becomes an issue, all right? And I mean, you're welcome to work through this and do it, but hopefully what happens is you start to hit all these walls and you think there's got to be a better way. And the good news is that there is. So let's actually go to the next page and see how much easier this becomes when we do this with respect to y. Okay, so let's just refresh our memory on what those curves actually were, right? We had x equals 3 minus y squared, and we had y equals x minus 1. And we know what they look like now. We've got this little sideways parabola happening here. All right, and then our line, all right, and the region between them. And that's where we're looking for area. And if you sort of turn this thing, if you rotate it 90 degrees, let me try to do that here, right? This is a much more straightforward integration problem, right? Here are the points at which they intersect. And now, oh look, right, we can just do top curve minus bottom curve. And it's as easy as that. All right, so let's spin this thing right back around and get to work. So the first thing to note, if we're going to be integrating with respect to y, we need both curves as a function of y. And the first one's already taken care of, right? This guy up here, this is already a function of y, so we're all squared away. But we've got some work to do on the second one, right? Right now we've got y as a function of x. This is not difficult, right? With just a little bit of algebra, I can write x therefore equals y plus 1. All right, so those are the two functions that I'm going to want to be integrating, right? If I'm integrating with respect to y, I should have two things that are a function of y. And you will very quickly notice when you set up your integrals, you'll notice if you've forgotten that step. So don't worry about that, all right? All right, let's come back over here. All right, and again, if I spin this thing around, I note that I still need my points of intersection. All right, but if we are integrating with respect to y, we will simply want the y values at which they intersect. So again, it's as simple as setting these two curves equal to each other, right? So we'll have 3 minus y squared equals y plus 1. And we'll solve, right? So let's see. I'll have y squared, let's see, plus y minus 2 equals 0. So that will give us, let's see, y plus 2 minus 1, which will give us y equals negative 2, and y equals positive 1. So actually, if we come back to this picture here, right, here are the y values where they intersect, right? We had found y equals negative 2 and y equals positive 1. And when we integrate with respect to y, it's as simple as top curve minus bottom curve, which in this case is blue curve minus red line, because the blue curve is consistently on top from y equals negative 2 all the way to positive 1. So we only need one integral, which already makes this way easier. All right, let's come on back and get started. All right, so for my definite integral, I know that I am going to be going from y equals negative 2 to positive 1, and I'm going to do top curve minus bottom curve, right? So relative to the y-axis, 3 minus y squared is on top, and my line, let's see, y plus 1, is on bottom. And so this is what I'm talking about. This is the step where you would know if you had made a mistake, right? It's just like u substitution, where if we are doing a u substitution, we want u to be our variable, we want du's, and we want u values in our limits of integration. Well, here, if we're doing things with respect to y, we want y as our variable, we want dy, and we want y values in our limits of integration. All right, so let's clean this up and wrap it up. So we'll have from -2 to 1, negative y squared minus 1 plus 2 dy. And then, let's see, that'll integrate to negative y cubed over 3 minus y squared over 2 plus 2y. And we'll evaluate this between -2 and 1. Okay, so let's give ourselves a little bit more room here, and this will give us, let's see, the value of this thing at 1 will be -1/3 minus 1/2 plus 2 minus the value of this thing at -2. So let's see, -2 cubed, -8/3, positive 8/3. All right, and then let's see, minus 2 minus 4? Yeah, double check me on that just in case. And then, all right, let's see if there's anything we could, let's simplify. Let's simplify our thirds first, right? Because -1/3 minus 8/3, that's -9/3. That'll clean up nicely. All right, and then 2 plus 2 is 4, plus 4 is 8, right? Minus 1/2 is 7.5. So you have -3 plus 7.5, which all works out to be 4.5. All right, so if it looks like, right, I mean, at the end of the day, right, rotate your page 90 degrees. If it looks like a very easy problem, if you change everything to be in terms of y, do it in terms of y. All right, thanks for sticking with me, guys. Enjoy the rest of your snow day. There are some suggested exercises so that you can practice all of this stuff, and email me if you have any questions. Adios.